Okay. So if we have two simultaneous equations and two unknowns, these are linear equations. No, they don't have to be linear. We can have any two simultaneous equations. If we don't know how to solve them rigorously, we can always graph them. Sometimes we resort to a graphing calculator, which I don't use in my courses. Okay. But you can graph the things in graphing calculator, see where the graphs meet. And there's your solution to the two simultaneous equations. Now, we just illustrate that with these equations. You know how to graph these. And I ask, is there a way you find the intersections of straight lines? Yep. Exactly what you do. So I'm not going to take time to ask you to do that, although anybody's watching this and trying to learn anything from it, I advise that you stop and graph these two equations. Okay, so the intercepts occur. The x-intercept occurs from y equals 0. The y-intercept occurs when x equals 0. So if we let y equals 0, 2x equals 10 gives us 5. That means the point 0, 5 is going to be on this graph. And then if x equals 0, y is going to be 5, y is going to be 10, so y is going to be 2. You know, I always do this. That point is 5, 0, not 0, 5. I know the difference. Letting y equals 0 and finding x, the 0 came first. My calculations 5, 0. I think that's why I do it, other than it's not all that right. Okay, so here we have 0, 2, 5, 0. And you can sketch a straight line through those points. Then 4x minus 3y, well, we do the same thing. Y is 0, 4x equals 12, so x would be 3. So I got them in the right order this time. And if x equals 0, y is going to equal -4. So -4, that's 2, and -4 would be down here a little. And now we sketch a straight line through these points and kind of miss this one. And any sketch is going to have a little inaccuracy, especially if you miss your points. We estimate then what the coordinates of this point would be. Well, if this is 3 and this is 4, if this is 5, then 4 would be about here, and 2 and 1. Okay, and if 2 is here on the y-axis, there would be 1, there would be 1/2, there would be 1/4. So we can kind of estimate if the coordinates of this point, if these are projection lines, appear to me to be about 3.7. One-half of 0.5. Now, really, the point should have been a little further to the left, a little higher on this line. Okay, so that should have been. So I think it's maybe more like 3.3.7 or something like that. Well, we're going to find out. So the next question is: we understand that we know how to actually solve these equations to get the exact solution. Okay, now to actually find the solution of this system, I'm going to number the equations 1 and 2. And I'm just going to go ahead and demonstrate this since you do remember having done it. Now there are various ways this could be done. you could solve both equations for X or solve both equations for Y. And then set the two expressions equal to solve for the other variable. You could solve one of the equations for X or Y. And then substitute the expression you get for, say you solve for Y, then you solve this equation, you're going to get 10 minus 2x all divided by 5. Okay, take that expression and plug it in for Y here, and then you have an equation with just x's. And you can solve it. Okay, those are important methods. Right now, we're going to emphasize the method of elimination. So what I'm going to do is I'm going to multiply the first equation by 2. Now, when I say multiply the equation by 2, I mean multiply the left-hand side by 2, multiply the right-hand side by 2. Because if I multiply the equation by 2, it's still going to have exactly the same solutions. It'll have exactly the same graph. Right? To multiply this first equation by, actually, let's multiply it by -2. And then write down the second equation. And then add the left-hand sides and add the right-hand sides. Let's see what we get. Okay, so everybody got that? Let's see if I can get it. If I know what the right answer is clearly you're going to get the right answer. You know, see if I get the same answer you do. Okay, so if we multiply this first equation by -2, well, we're going to have -2 times 2x plus 5y. That's going to give us -4. That's minus 10y. And then -2 times the right-hand side is going to give us -20. Second equation remains as it was. So if I add these two equations, the -4x and x give me 0. Then it's minus 13y equals -8. And then we easily solve this for y. We get y equals 8/13. Am I right so far? Okay, good. Now, okay. Now, the way I often, almost always try the next step is I go ahead and circle this. And I'll bring this back and I'll plug it into one of the equations. Easy to get the arrow to the y in the first one, so I just chose the first, I could have chosen the second one just as well. And that brings me down here and gives me the equation. Two x plus 5 multiplied by 8/13 equals 10. And this is the equation we can solve for x. And when we get it, then we're going to take our complete solution and put it into the second equation. We haven't, you know, whichever equation we didn't substitute the y into. Okay. So we multiply both sides by 13, and we get, and I'll write this out. Multiply both sides by the only denominator we see. With more than one denominator, we use a common denominator, preferably the least common denominator, but any common denominator would really work. Save ourselves a lot of energy, but use the least common denominator. But in this case, there's only one denominator. We multiply both sides by that, and we get 26x plus 40 equals 130. So that 26x equals 90, and x equals 90 over 26, which reduces down to 45 over 13. Did I get it right? Okay, good. 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 This is a good day for me. Okay, so let's write it out explicitly. The x is 45 over 13. Our solution. The system can be written as 45 over 13. Eight over 13. You know, that doesn't agree very well at all with what I had here. 45 over 13. Yeah, actually, no, 45 over 13 is 3 and 6/13. It's about 3.5. Now, my estimate was 3.7. I said, if this thing is back here, it'd be more like, I don't know what I said, maybe 3.3 or 3.4. Well, it turns out it's between 3.4 and 3.5. At 8/13, well, our estimate was 0.5. Okay, 8 over 13 is 0.6, about 0.16. Okay, no, wait, it was, yeah, 16. Okay, instead of 0.5. So the actual, just so we can compare the decimals. Let's say, yeah, I don't know if it's 3.4 or 3.5, but approximately 3.5, and this is about 0.62. Now, the approximate solution. Agrees decently. With what we have up here. And that confirms that we probably didn't mess up. At least if we messed up, that we lucked out and didn't mess up too badly. Excuse me, a little hoarse. As I said, we could have solved this system in various ways. Okay, one way would be to solve one equation for one variable. Take the expression we get for that variable, substitute it into the other equation, and so forth. Sometimes that's necessary. So we've just talked about compound interest in the exponential functions that are involved in it. Okay. And we have equations like that. Maybe look at something like this, okay? If we had a situation, this would correspond to a situation maybe where we have 12% interest compounded 4 times annually. I think you might want to think through some kind of function. What that would be the model. Okay. Where we start with $1,000 and so forth. Here we start with $500 and compound 10% interest one time annually, one time a year. Okay. This is a standard form of an exponential function. So in general, an exponential function could be written as y equals a times b to the t. Well, let's say we have 2 points on the graph of an exponential function. Exponential functions have an independent variable t. Let's say that the coordinates at this point are and again, I write down the first variable that I'm thinking about as well as the first coordinate, but that's not what we want. Okay. I'm going to have to label it down here. Let's label this on 2700, 20,700, and then this one would be about 50. Not very realistic in the scale of the graph. It'd be more like 14 to 1500. Oh, this is okay. Now we expect that this is something that behaves exponentially. Maybe it's a population, maybe it's money, one thing or another. And I can try to draw a reasonable graph of an exponential function through these points. Now we want to say then that this function is y equals a b to the t. And what we want to do is find a and b. So if this is a population, we can predict what the population will be at some point in between them. If we've got a really good graph, of course, we can make a prediction from the graph. I want the population at t equals 30. Now 30 might be over about here, come up here, over here. This is 700 and this is 1600. I might get this in the graph a population of 978.329. Now that's what it is according to this graph. I have a better eye than most people. Well, seriously, we can make that prediction from the graph. If this is the value of an investment that we know has been growing at a constant interest rate and will continue to do so, then we can find not an exact value at any given time, but a value to any degree of precision we want. So if we want to find it down to the 10 billionth of a cent, we could do that. Okay. If it's a population of something that's going to be responding to various disruptions of one kind or another, maybe good disruptions, maybe bad ones, then any prediction far into the future is going to be pretty fuzzy. Okay. And maybe a hand-drawn graph will tell us everything we need to know. Everything that's, a good, well-sketched graph will give us predictions that are probably about as good as anything we could get by doing the math. by doing the algebra. I mean, we're doing that.
Right.
And of course, we can always use technology to get a good graph and look at good features. Okay. So we have all those options. Well, what we can do in order to find A and B is we can plug 2,700 into this equation. Okay. Now let's talk about this for a second. I'll turn the camera off. Okay, so yeah, we did really well with that. We knew exactly where the 20 would go and where the 700 would go and where the 50 and the 1,600 would go. So using the first point, we get 700 equals A, B to the 20. Second equation, we get 1,600 equals AB to the 50. So there are various ways to solve this. The more standard way is to solve one equation for one of the variables. Of course, the variables in this equation, the unknowns in this equation, are A and B. Okay. So is it easier to solve, say, the first equation for A or for B? Well, the answer I got was immediately, well, solve it for A. B's got that exponent on it. We don't want to deal with that. We know about logarithms. Then we would need, well, we wouldn't need logarithms, but we'd end up having to take a 20th root. And we can do it, but we're not going. Okay, so we solve equation 1 for A, and we get A equals 700 over B to the 20. Plug into the second equation. Then we get 1,600 equals 700 over B to the 20th times B to the 50th. Now, can we simplify this equation and hopefully even solve it for B? And that might be infringing on unfamiliar territory. We'll see. All right, now, first of all, we have this. How do we simplify this? Well, I kind of did a few steps over here. Okay, we got 700 over B to the 20th times B to the 50th. It's a little small and not really well, but I think we know what we're doing. Okay. Now, B to the 50th could be written as B to the 50th over 1. So we have two fractions. And this product of the numerators will be 700 times B to the 50th. Product of the denominator will be 1 and times B to the 20th. We could switch the 1 and the B to the 20th so that B to the 20th is matched up with B to the 50th and the 1 is under the 700. So I could even write that, put this over 1, put this over 1. And we can see that the numerator and denominator of the product of these fractions will still be the same. So that we don't really need the 1 on the 700. And then also B to the 50th over B to the 20th. So, you know, get in the habit of doing mathematics by the way it looks, but they don't understand why it looks the way it does and why it changes the way it does. And they get confused about when it looks this way, you do this, when it looks this way, you do that. You want to go back to the principles. And the principle is, and I know everybody here understands it very well, but b to the 50th over b to the 20th means you write 50 b, b times b times 50 times. And you write it 20 times in the denominator. And 20 of those in the denominator can match up with 20 of the ones in the numerator. So you'd have a 30 b's up here. And then you have 20 b's matched up with these 20 b's, leaving you 30 b's. Now there are rules, and if you're really conversant in those rules and confident in them, you can use them. But when you use those rules, you should always be thinking about what's really going on. Now sometimes, yeah, you think back to simple examples like this to avoid making embarrassing mistakes. You can see me make them all the time, but you don't see me make that one. Okay. Okay. So 700 b to the 30th. So this right-hand side comes down to 1600 equals 700 b to the 30th. Now we bring this over here. And we divide both sides by 700, and everybody did that. Everybody got to this. You know, I had to confirm a little bit about that b to the 30th thing, but that was the instinct. We're going to get that. And then immediately divided by the 700. So this would just b to the 30th equals 1600 over 700, which is 16/7. Now we're at a point where we're not quite sure what to do. Okay. And the impulse was to use logarithms somehow. And it mentioned base 10 logs. Good thing. Very good that you know that because it was in your curriculum. Okay, I don't think it's in our local curriculum, or if it is, our students are not. So, okay, b to the 30th equals 16/7. What do we do? I say we apply the rules of exponents again. We do b to the 30th times the 1/30th. Equals 16/7 to the 1/30th. Now, what's b to the 30th to the 1/30th? What do the rules of exponents tell you? And let me comment again about the idea of logarithms. You can definitely solve this using logarithms. Okay, it's kind of overkill because you can do this, but even though you could solve that using logarithms, right? You get 30 times the log of b equals the log of 16/7. Divide the log of 16/7 by 30. And you get the log of b, then you do whatever your base is to that power, and that gives you b. Okay, it's base 10 by that power. So you can do that. It's good. But not doing that yet. Okay, so anyhow, we get it down to this. What do we do? Like, how does that simplify? And if you can successfully simplify that, you'll understand why we use that step. Okay, so now what I saw you do, which was very good, you just change this to radical notation. Okay. You didn't really simplify this, but you did find the solution. It's going to be the 30th root of 16/7. Okay, and 30th root. Use your calculator. Okay. However, I want to emphasize the exponent. So how do you simplify b to the 30th to the 1/30th? Okay, so when I asked how do you simplify this, I just immediately got the answer, b to the 1. Because the rules of exponents say when you have a power of the power, you multiply the exponent. So we get, all right, this out. Running out of room, but I maybe can get away with it. This is b to the 30 times 1/30. That's 16/7 to the 1/30th, and 30 times 1/30th is 1. We get 16/7 to the 1/30th. Now, you probably can't do a 30th root in your head, and I can't do it all that accurately in my head, but it's kind of fun. So 7 into 16 is pretty close to 2 1/4. And the square root of 2 1/4 is 1 1/2. Okay. And then the square root of 1 1/2 is about 1.23. That would be the 1/4 power. Okay. Now we're getting into the realm where it's pretty easy to estimate square roots. The square root of 1.23 is pretty close to 1.1. It'd be the 1/8 power. Square root of that is about 1.05. The square root of that is about 1.25, 1.025. I've kind of lost track because I was talking about it, whether I overestimated or underestimated some of these. I'm going to hazard a final guess and say 1.027, just to see if I'm right. And if so, I'll explain exactly what I was thinking. Okay, well, somebody showed off their calculator, and their calculator turns out to be fairly accurate. Okay, except the calculator gave like 1.0279, and then some other stuff. So it got to 2.7, but it really runs off to 2.8. I'm a little embarrassed by that. Okay. I'm not going to digress to explain what I did there, but I will if I get a chance. We have time later. Okay, anyhow, we get B. And okay, it's about 1.028. And really, I really wrote an 8, but it's not as good an 8 as I usually write. Well, okay. We'll correct that to 1.028. And of course, there are more decimal places. So if you're wanting to calculate the value of a loan, given this information, you want to do several more decimal places if you want to get it down to the penny. Okay. I'd use all the decimal places your calculator will provide you, although you don't really need that. But that would give you pretty accurate results. Okay, so we're really good. So we've got B. And also we've got a lack of George, please. There's a little range from here. Okay, so now we know that yeah. Okay, this system, through the steps that we show here, gives us B. Approximately 1.028. So what do we do with that? We normally take a piece of blue chalk. And we plug this into one of our equations. Don't think I'm mistaken this time. And now we have 1600 equals A times 1.028 to the 50th. Well, that's easy to solve for A, so go ahead and solve it. Okay, so now remember that B is only approximately 1.028. You kind of want to remember that, so you can always ask yourself, how many significant figures do I need in that number to get an accurate result here? Well, I'm raising that number to the 50th power. That's a little bit of a stretch, okay? So what we're going to get is not going to be all that accurate. I use little wavy equal signs to indicate that these are approximations. Okay, now you plug that into your calculator, and you got 400. Pretty close to 400, 402 or something like that. Okay. So now y equals AB to the T. Now this is an approximate model. But it will hit those two data points, and it makes good sense in terms of the picture. Well, actually, it won't make really good sense in terms of the picture because these points aren't real accurate. If this is 20 and this is less than 50, okay? So the picture wasn't great. And if we look at where the picture indicates we cross the x-axis, well, let's see. If this is 700, well, it isn't too bad. It looks like this is more than 500, not more than 400, less than 500. I would estimate from the graph maybe 450, but maybe I would estimate 400. Okay, not too bad. This point is 0,400. So maybe we want to know how much the initial investment was if it was made at T equals 0. Okay. How many we have? So this allows us to fit an exponential function to any 2 points on a graph. So if I observe a population, if this is a population, well, our model is not going to be all that exact. Okay, and rounding off to 1.028 is reasonable. Okay. Okay, well, let's interpret. That's your initial amount. What's the 1.028 tell you? Let's assume this is an investment. Now, in terms of the development we did with compound interest and understanding where that compound interest formula came from. If we're used to looking at that, we can see that 0.028 corresponds to 2.8% interest compounded annually. Annually because T, okay, instead of 2 tier, 3 tier, 4 tier. Okay, so rate is 0.028. Our multiplier, okay, is 1.028, or our growth factor. Our growth rate is 0.028. Okay, now I need another adjective in front of growth. Okay. And the adjective I'm going to need is the effective. Annual growth rate is 0.028. Or 2.8%. Now, it could be that this is maybe what we would get if we had 10% compounded 4 times annually. Probably just a little more than 10% compounded 4 times annually. We give us an effective annual rate of 2.8%. And really, if this is this could be a continuous growth rate. Okay. And I'm not going to make the transition to continuous just because we don't have we've got a fairly good chunk of time left. I don't want to use it for that. Okay. But this would be pretty close to e to the 0.028 t. Okay. But I think that'll take us a little further than we really want to reach today. Okay. Just knowing that it's the main thing I want to get across. This important process. Okay. Now there's another one. Since you already know something about logs. What if we assume that these same 2 points are the graph of a power function? Okay, now how far to make it go? Uh-oh, yeah. Camera's not showing me anything. We move it about here, yeah, there's nothing. Power function model is of the form let me think about how I want to make sense of this before I write it down. I want to relate it to our basic functions, okay, our toolkit functions. Okay. I decided I wanted to put this in context before I wrote the formula. We can see the difference between this and this. You're familiar with power functions because y equals x squared, one of our toolkit functions, is a power function. Y equals x cubed. And y equals 1 over x is a power function. I can write that as x to the negative 1. It's x to a power, right? Okay, so these are examples of power functions that we know. 1 over x or big x to the negative 2. It's x to a power. So now when I write down the general form of the power function, I'm going to write it as y equals ax to the p. If p equals 2, we have this 2 function. P equals 3, we have the cubic function. If p equals negative 1, we have the reciprocal function. If p is negative 2, we have the reciprocal square function. And this contrasts with our toolkit exponential function where x is in the exponent. Okay, so now we want to try to fit the data that we have this one. So can you write down the simultaneous equations and then think about what you would do to solve them? Okay, so you did very well then, very well. So, okay, so we plug 2700 in. Well, 20 is going to be x, 700 is going to be y. We're going to get 700 equals a times 20 to the p, and 1600 equals a times 50 to the p. Well, let's solve the first equation for a. And I'll do this kind of briefly. We'll write out total equation every step. But a is going to be 700 over 20 to the p. Then we'll take that and plug it in for a. And we're going to draw my arrows here because that's easy to see. We're going to take up much more space we can get short. I've got it. Okay. And we get 1600 equals 700 over 20 to the p multiplied by 50 to the p. Okay. Now, out of space here. So we'll move on up a little higher on the board. So we get 1600, I'll just rewrite it, equals 700 over 20 to the p times 50 to the p. And this becomes 1600 equals 700 times 50 over 20 raised to the p. Okay, we want to solve for p. How do we do that? Well, unlike the previous solution for the exponential, we can't use just our basic algebra. We have to use logarithms to get this. Okay, so I'll just sketch that kind of quickly to remind you, because you've already done it. You are very near to remembering what to do, so it might be familiar to you. It might be, you might find it kind of neat. Okay, so first of all, I'll write this as 1600 over 700 equals, now 50 Okay, well, actually, you didn't do this step, okay? Hang on a minute. Let me, what I saw, because here's where we ran into a little bit of a glitch, and I kind of skip ahead. Okay, you got this. Okay. Now, the rules of exponents, this is the same thing as, okay, 50 to the p over 20 would be both the same power. You write that as 50 over 20 to the p. And you know that rule. Okay, you recognize it. You totally believe it. You just didn't think of it right at that time. Well, you can't think of everything. Okay, and that's fine. I anticipated that might be stuff with the point where you not be sure what to do. You haven't done it for one. Okay, 1600 equals 700 times 2.5 to the p. Now, ordinarily, I don't like working with decimals when we can work with fractions. However, at some point, it often becomes necessary to go to the decimal. We don't want to do that too early. In this case, though, we get an exact. Actually, I'm going to keep it in fractions. The difference at this point. Of course, 50 over 20 is the same as 5 halves. So now we can write 5 halves to the p equals 700 over 1600. And that's pretty close to 0.4. Keeping the fractions away. Not sure how you solve this. If you take the log of both sides, you can write the equation like this. One of the rules for logarithms you might recognize, although maybe not, the log of a quantity, the power is equal to the power times the log of that quantity. You see that rule? Okay, good. You've been extremely well prepared. Okay, so the p equals the log of 7/16, we don't need those zeros, divided by the log of 5 halves. And you have log keys in your calculator. You have log and natural log keys. Okay, doesn't matter which one you use, as long as you use the same one for both the numerator and denominator, but you calculate that and you get a result. So we are out of time, but just take a minute to see what the result is. Right now, what that's the calculator is about 4. I don't think that's right. I'm getting, okay, if I use a base 2 log, 7/16 is close to a half, that'd be about the -1 power. 5 halves is a little more than 1. So I'm getting something a lot closer to the first power. We check the calculator. We got something maybe 1.1 or 1.2. Put a big question mark on that, but we're out of time. We see how to solve it. No, actually, it would be a negative power. Okay, yeah. -1 power, but I'm getting something close to -1. I think a -1 give you -1. -1. Get something like 1/2. I don't know. I don't know. Don't have a good estimate for that one that fits my intuition with that graph. The graph of the fractional power looks something like this. And you can see a graph of that shape. No. Okay. Yeah, you go up here. Yeah. Don't have a kind of a negative. Okay, but anyhow, we'll let you go. And hopefully that was interesting.